Okay, so our next speaker is Silvia Pascoli, who's going to tell us about neutrinos.
Thank you very much. So I'm going to talk to you about the only known component so far of dark matter, which are neutrinos. And so as you know, neutrinos have seen in the past 15 years a large change in our understanding of the properties, because in 1998 we discovered at high significance, more than 5 sigma, the neutrino do oscillate. And this implies the neutrinos have mass and mix. Now, what has also happened in the meantime, that cosmology has become one of the main probes of neutrino masses, and I'm going to talk about that more later on. So first of all, I will discuss neutrinos from the particle physics point of view. I'll focus on the neutrino masses. So starting from neutrino oscillations, I will look, first of all, why that is so important from a theoretical perspective. I want to underline that determining the neutrino masses, and in particular, if neutrinos are Majorana-Dirac particles, as some papers in cosmology have started looking at combining that with neutrino-less double beta decay, has really very fundamental implications for how we understand particle physics, in particular, how we extend the standard model to explain neutrino masses. So I think we should not underestimate the impact that the cosmological observations together with the particle physics searches can have for our understanding of neutrino, but more in general, particle physics interactions and fundamental particles. So I'm going to look then at how we measure neutrino masses from the particle physics perspective. This is where I'm going to focus probably most of the time during this talk. And then I will compare that to what can be done in cosmology. Planck has already put very strong constraints, but there are even more exciting prospects for the future. And then I want to draw some comparisons and looking at the complementarity between these searches. When we combine them together, we can actually draw quite strong statements out of it. So let me come with what I'm sure you already know, that the neutrinos do oscillate. Now, the oscillation probability can be computed, and that depends on the mixing angle, theta, between, this is the disalignment between flavor states and massive states. Now, flavor states are the states that interact according to the standard model. So this is the way I produce a neutrino. In an interaction, I will produce a flavor neutrino. It could be an electron neutrino if it is associated to an electron, a mu neutrino if it is associated to a muon, etc. And this is also the way I detect the neutrinos as flavor states. But they travel as massive states, states which have a definite mass. The two bases are disaligned, misaligned, so there is a mixing which relates the two. And like, for example, in any quantum mechanical system in which you produce a state which is not an eigenstate of the Hamiltonian, this will lead to an oscillatory pattern for the probability of detection of the particle. Spin precession, for instance. This is exactly what happens here. So this is the mixing, this is the disalignment between the two bases, the flavor base and the massive base, and this is the mixing the masses. Now, because each mass state will evolve with a certain phase, now in order to generate a different type of flavor state, you need the different phases not to correspond. So for that, one needs different masses. So this is the way neutrino oscillation imply that neutrinos mix, and from the perspective of this talk, neutrinos have mass. And this is really very important, because at least in the standard model, neutrinos don't have a mass, and I'll comment on that in a couple of slides. So for me, this is the first evidence that we have of physics beyond the standard model of particles. So this is the knowledge. The parameters which always control neutrino oscillations are mixing angle and mass square differences. So this is the way we analyze the data and we report the results. So there are two mass square differences, delta m square solar and delta m square atmospheric. As you see, they are very different. This is around 7.5 10 to the minus 5 eV squared, and this is around 2.4 10 to the minus 3 eV squared. So it's roughly a factor of 20 between the two. And then there are various values for the mixing angles. This is the latest one which has been measured last year, but this is not really a focus of this talk. So let's think about in terms of masses. When we have two very different mass square differences, means that we need to have three neutrinos, three massive neutrinos that we can arrange in two different ways: the normal ordering and the inverted ordering. So as you see here, the two lightest neutrinos are separated by the small mass square difference, the solar one that I showed before. And we can express the three masses in terms of this minimal mass and the mass square differences which are known. So Already in the cosmology literature, people talk about the normal hierarchical spectrum. What they mean is normal ordering plus negligible mass. So in this case, you see that there is quite a difference between these masses, and the biggest one is M3, which is given by the square root of delta M square atmospheric, which is around 0.05 electron volts. In the inverted ordering, the two heaviest masses are nearly degenerate, and in this case, because they are more or less given by the square root of delta M square atmospheric, this in the inverted hierarchical spectrum. So if you look now at the sum of the masses, now you have 0.05 here, 0.05 here, so 0.1 electron volts. So this is the prediction in the case of the inverted hierarchical spectrum. Notice also that this minimal mass in either case could be comparable to the delta M squares. So there is an interpolating regime between the case in which we can neglect the minimal mass and the case in which instead we can neglect the mass square differences, which is the quasi-degenerate spectrum. This is what current cosmological observations and also particle physics observations can actually test. So in order to determine the masses, which is what we really need from a theoretical point of view, we need to determine the ordering and we need to determine the absolute mass scale. Why is this so important from a theoretical perspective? So as I already mentioned, the standard model, at least in its simplest form, doesn't allow for neutrino masses. This is because the way we write down a mass term for the other fermions, electrons for instance, requires two different types of fields, a left-handed field and a right-handed field. Now this, well, you might notice this breaks SU2. In fact, the way we actually write down this term is by coupling the left-handed doublet to the Higgs. And when the Higgs gets a VEV, now we generate the neutrino, the electron mass. Now, for neutrinos, there are no right-handed neutrinos. So we can introduce them, but that has problems, as I'll show you in the next slide. The other possibility is to have a Majorana mass term. So this uses only left-handed neutrinos, but the problem of this term, this breaks SU2, so is not allowed in the standard model, but could arise from higher theories, as I'll show you. So the reason why a lot of theories don't like the explanation of Dirac masses for neutrinos is that now if we do what I already said before, we couple the left-handed doublet to the Higgs and the right-handed neutrino to generate neutrino masses, that the mass will depend on the coupling between the Higgs and the neutrinos. And the coupling needs to be extremely tiny. Now, when we look at masses in the sub-eV region, the coupling needs to be smaller than 10 to the minus 12, 10 to the minus 13. Such value is somewhat unnatural from a theoretical perspective. A lot of theories don't like that unless there's a way to explain why it is so small. And some, for example, some examples in extra-dimensional models have been put forward. So what instead theorists very much prefer are Majorana masses. So Majorana masses actually could come from a higher energy theory. Now, if we look at the dimensions, so now this is the SU2 conserving term that I showed you before. I'm coupling the left-handed doublet with the Higgs, and when the Higgs gets a VEV, this generates a Majorana mass term. Now, the dimension of this term is 5, so one needs to suppress in the Lagrangian this term by mass here. And so the way we can look at it is that if we had enough energy to zoom in for these interactions, what we would see is a virtual particle being exchanged. A virtual particle that are very high scales. So this is what, for example, seesaw models do. So now in this case, we don't need very tiny couplings with the Higgs. We just need a very heavy mass to be exchanged. And this generates very light neutrino masses in what is considered a natural way. So now, what can be the particle that can be exchanged? Well, that depends on the type of extension of the standard model. So the simplest case is which we exchange a singlet fermion in between. This is the seesaw type 1, which is somewhat the standard extension for neutrino masses. But there are many other possibilities. For example, one can exchange a scalar triplet, a fermionic triplet, and there are many different extensions which have been looked at. Clearly, the question is, what is the new physics scale, the new energy scale, so where the new particles and the new interactions will be there, but that is a completely different story. Let me give you one example. This is the simplest case, the simplest extension, which is seesaw type 1. And this, for example, can be easily embedded in gut theories, so grand unification theories where the couplings merge together at some very high energy scale. Now, one introduces a right-handed, very heavy particle, a right-handed neutrino, and one allows for a perfectly SU2 conserving coupling between the left-handed doublet, the Higgs, and this very heavy neutrino. Here, the coupling doesn't need to be very small, can be as large as the other, for the other fermions. For example, this could give a Dirac mass of the order of the GeV, like for the tau, for all the other quarks. The point is that this heavy right-handed neutrino can have a mass, a Majorana mass term, which is very, very heavy. And when I diagonalize this mass matrix to find the values of the neutrino masses, I see here this very heavy mass suppression at work. So if I want to take Dirac masses in the GeV range, and now I assume that this mass scale is close to the gut scale, 10 to the 14 GeV, then I get neutrino masses in the EV scale, which is what I want. So that's why people consider these type of models very natural. They can be easily embedded in gut theories, and they give us the right values of neutrino masses without requiring tiny mixing angles. Now notice that this is a Majorana type of mass now, and is very different than from what I discussed before, the Dirac masses. So the kind of extension that I do of the standard model in order to understand neutrino masses really depend crucially if you're talking about Dirac versus Majorana. So one has to keep in mind that the implications of such determination are really very important from a theoretical perspective. So now, how are we going to determine neutrino masses? So there are different strategies which are employed in particle physics, and they give different type of information. So we have neutrino oscillations. These are sensitive to the ordering. Remember that if the two lightest neutrino masses are the lower ones or the heavier ones. We have direct searches of the masses. This is, for example, Catherine, which is going to take data in a couple of years. And we have neutrinoless double beta decay. So let's look at these one by one, starting from neutrino oscillations in long baseline neutrino oscillation experiments. So now when neutrinos travel in one of these experiments, now they are produced in an accelerator complex, for example, let's say a MINOS in the US. They are produced at Fermilab, but then they travel hundreds of kilometers before they are detected, for example, in the MINOS experiment or NOVA experiment. So because the Earth is curved, clearly they go through a large amount of matter, and matter is made of electrons, protons, and neutrons, and not their antiparticles. So what one expects is that there are these effects which change the effective mass of the neutrinos in matter, and these effects depend on being particles or antiparticles. So the effects will be different if we are looking at neutrino channel or the antineutrino channel. Now, specifically, the oscillation probability in matter depends on the mixing angle, which is changed here. This is the mixing angle in vacuum, and this is the effect of matter. This is the number density of electrons in matter that we know quite well. It just depends on the density of the Earth, which is around 3 grams per centimeter cubed. So notice this formula here. This is for neutrinos. For antineutrinos, we have a plus sign here. So now, in particular, there is a point in which these two terms in the denominator could cancel out with each other. And that depends on the sign of delta m square. Now, if we go back and look at the normal ordering with respect to inverted ordering, here, delta m square, which is m3 squared minus m1 squared. In this case, this is positive. In this case, m3 squared minus m1 squared is negative. So the sign of the delta m square relates directly to the type of ordering we have, normal or inverted ordering. So if we go back to this formula for the mixing angle in matter, you can have an enhancement of the probability, which depends on the mixing angle in matter, if delta m square is positive. If instead delta m square is negative in the inverted ordering, then I cannot have here a cancellation, and I have just a suppression of the probability. So I can go and measure the probability, and I can try to see if there's an enhancement or a suppression. And in particular, I can compare that with the antineutrinos, where I have a plus sign. So I will have the opposite case. I will have an enhancement in the inverted hierarchical case and a suppression in the normal hierarchical case. And you can see this here. This is the probability of oscillation. This is for a baseline of 1,300 kilometers as a function of the neutrino energy. And this is the probability for the normal hierarchy. And this is for the probability for the inverted hierarchy. And you see this big difference, which comes in by these matter effects that I already just mentioned. So these matter effects are being used by atmospheric neutrino oscillations. And what has changed kind of all this discussion in the past year has been the discovery of theta 1,3. Now, these effects, actually, we can see it back from this probability here, this expression here, depend on the mixing angle. And for these experiments, depend specifically on the mixing angle theta 1,3. Now, last year, we had the discovery of theta 1,3, and actually we measured it to be quite large. So all these effects are enhanced with respect to what we thought a couple of years ago. And so indeed now, experiments like atmospheric experiments like penguin ice cube, for example, will be able to have sensitivity to the mass hierarchy, at least at some confidence level. Where we are going to have probably the most robust confirmation of the mass hierarchy is via long baseline neutrino oscillation experiments, because in this case we control very well the energy spectrum, the distance, and all the various effects. Now, it's true that this enters together with the CP, the determination of the CP phase delta, but at the same time, because theta 1,3 is so large, the generacies that before were thought to be very important in determining the mass hierarchy, in reality are going to be subdominant, at least for determining the ordering of masses. So the experiments that we can look at are super beams, and there are two which are already running. One is T2K, which has a month ago provided 7 sigma evidence for theta 1,3, and NOVA, which is due to start any day now. We should have started a month ago, so it should start in a few weeks with a beam. And then there are plans, more kind of ambitious plans for the future, LBNE, SPL, Laguna, LBNO, etc. Super beams are essentially extensions of current running experiments like MINOS. The way we produce the neutrinos are in pion decays, and then because the pions are accelerated at high energies, that produces a beam of muon neutrinos. And one looks for the change of muon neutrinos into electron neutrinos, which is sensitive to those probabilities that I showed before. If one wants to go to kind of even more ambitious and precise experiments, one will have to go to a muon factory, neutrino factory, where neutrinos are produced from muon decays. And so, but that is sometime for the far future. So this is what T2K and NOVA can do in the next 6-7 years or so. As I said, there is some degeneracy with the delta phase. So this is the mass hierarchy discovery, and you see that that can happen for roughly 40% of the values of the delta phase. So without going into the details, this tells us that there is some chance that the mass hierarchy can be determined at a couple of sigma in the next 6-7 years. But if we really want to be able to determine that with more confidence, we need to go to these other experiments that I already mentioned. LBNE, for example, this is where the beam will be produced at Fermilab and will travel 1,300 kilometers to the Sudan, to the home stake mine. Now, these experiments are currently under discussion, and so the next couple of years will be critical in seeing which directions we will go. And this will determine the hierarchy at 5 sigma in a few years. So now, long baseline neutrino oscillation experiments determine the mass hierarchy, but now the other very powerful probe we have is neutrinoless double beta decay. I mean, the main physics goals of these experiments are the determination of the nature of neutrinos, whether they are Dirac or Majorana. But in doing so, can they also give us information on the neutrino masses? Now, neutrinoless double beta decay is a process in which 2 neutrons go into 2 protons and 2 electrons, and they exchange this light virtual Majorana neutrino here. And the half-life time depends then on the neutrino parameters, in particular the masses, the mixing angles, and these phases here, which are called the CP Majorana phases, on which we have no information, no we will ever have. So these need to be treated completely as free parameters. So depending on the values of the masses, we can have different values for this parameter which controls the half-life time. This is called the effective Majorana mass parameter. So in the case of normal hierarchical spectrum, which I remind you is M1 much smaller than M2, much smaller than M3, you see that here the terms are all very small. This is small because it's controlled by delta m square solar, and this is small because it's suppressed by theta 1, 3. So the predictions for M effective are in the few milli-electron volt region. Now, in the inverted hierarchical spectrum, instead, the dominant contribution comes from the delta m square atmospheric. So we are in the few tens of milli-electron volts. And if we are instead in the quasi-degenerate spectrum, then in this case, the mass is controlled by the common mass, so it's quite large. So as you see, as the predictions are different, now if in an experiment I measure this effective Majorana mass parameter by measuring the decay rate, then I can kind of try to reconstruct in which spectrum I am, and I can actually compare that with cosmology. So now if I allow the minimal mass to vary continuously, these are the regions I obtain. This is the effective Majorana mass parameter. This bluish and red region here corresponds to the inverted ordering. This yellow and red corresponds to the normal ordering. So, and experimentally, we are here right now. There has been this year quite a few new results, EXO 200, Kamlan-Zen, and Gerda, which have brought down the bound roughly to 0.2 electron volts. But there are plans to go down by a factor of 10 and even possibly more so probing the region. So now imagine that you find, for example, an experiment which gives us a value of M effective in this region here. We would know that we are in the inverted ordering, or for a tiny value, tiny range of the masses in the normal ordering. If we don't find anything down to 10 milli-electron volts, then the only possibility is that either neutrinos are Dirac particles or the ordering is normal. And notice that in that case, this is the prediction for the normal hierarchical spectrum. But if the masses, if there's some partial degeneracy, we could have even a perfect cancellation or values which are much larger. So depending on the value of a min, we have various possibilities. I'll come back to that right at the end of my talk. So I already mentioned that it's possible to extract information on neutrino masses. For example, if M effective is bigger than 0.2 electron volts, then we know that the spectrum is quasi-degenerate. But now this is start being at kind of constrained by current experiments. And the other important point, if we don't find anything down to 10 milli-electron volt, we know that the ordering is normal, or neutrinos are Dirac particles. The other, I want to make here a point. These constraints and this measurement of neutrino masses have some possible model dependence. Now, looking at neutrino double beta decays through line neutrino mass exchange is the simplest case, and the most natural case as well. However, neutrino double beta decay could be mediated also by other mechanisms, and so there could be the cancellation that contributions from light neutrinos and other mechanisms cancel partially out, or neutrino double beta decay is due mainly to these other mechanisms and not from light neutrino masses. So there is some model dependence here that one has to keep in mind when one trusts the constraints on neutrino masses. It's also to be said that most of the other mechanisms, as far as the masses are quite heavy, the masses of these new particles which are introduced are heavy, they tend to be suppressed with respect to the light neutrino exchange. So it's very difficult to arrange for models in which the heavy physics contribution dominates with respect to the light neutrino ones. So there is some model dependence, but it's also true that light neutrino mass exchange remains the simplest and the most natural explanation if we see neutrino-less double beta decay. And the way we look for it is that this is the two neutrino double beta decay spectrum. So one measures the energy of the electrons coming out from the decay. And this is a measured spectrum for many nuclei. Right at the end, as there are no neutrinos carrying away any energy, the two electrons need to carry away all the energy available in the decay. So it's going to be a small peak right at the end of the spectrum. And by looking at this feature, now that we have already strong constraints, for example, this is what we would expect from EXO 200. This is the double beta decay. And here, right at the end, one would expect a tiny peak. As you see, these are not easy measurements to do because there are lots of backgrounds, but they are quite well understood. And in this way, one can put constraints on the half-life time and conversely on the effective Majorana mass parameter at the level of, as I already mentioned, 0.2 eV for the masses. What is also exciting is that there are many experiments which are going to be planned for the future, SNO+, NEXT, Majorana, Cobra, Super Nemo, etc. So these bounds are going to improve very significantly. The only model-independent constraint on neutrino masses come from beta decays. Now, in beta decays, one looks at the spectrum of electrons coming out of the beta decay. If neutrinos have a mass, we have this specific change in the shape of the spectrum right at the end. Because also in this case, the electron, if neutrinos are massless, can take away all the energy, while instead, if the neutrinos have a mass, they will be able to take away all the energy minus the neutrino mass. And so by looking at this tiny change, one can put constraints on neutrino masses. Here, there's no model dependence. If neutrinos have mass, we expect to see this. And so these bounds are the strongest and most robust that we can possibly have. The problem is that they're also somewhat the weakest in the sense that this is Catherine. Catherine is under commissioning, is going to start taking data in 2015. And this is the 90% limit on the neutrino mass as a function of time. So once they start data taking, immediately, within a few months, they will reach the 0.4, 0.3 EV sensitivity, which is going to be important to compare to what we see in cosmology. And their ultimate reach is going to be down to 0.2 EV. Going beyond this is very difficult, and there is some R&D happening for other type of searches, but indeed, this somehow we have reached probably what is the bound, the limit for these type of searches. So just as a summary from the particle physics point of view, we have neutrino oscillation experiments which, by looking at matter effects, can determine the mass hierarchy. I haven't mentioned that also reactor neutrino oscillations, by looking at the small effect of delta M square atmospheric over delta M square solar oscillations, can also determine the mass hierarchy, and this is what Juno and Reno 50 plan to do. Now, beta decay experiments, as I already mentioned, these are the most robust, but they can probe neutrino masses only in the quasi-degenerate spectrum. And then finally, neutrino-less-double beta decay is very sensitive, but measure a combination of masses and phases. So somehow one has to keep in mind that what one can extract is some information on the combination of these parameters. How much time do I have? 10 minutes, thanks. So now let's look at cosmology. Now, neutrinos were in thermal equilibrium early on. They decouple around 1 MeV. And since then, they really don't do much. They redshift. Now, they impact on Big Bang nucleosynthesis quite significantly. And then they contribute to the relativistic energy density of the universe, till they become non-relativistic when the temperature drops below their mass. So they will affect the CMB, and they will affect the meta-power spectrum. And these are the two ways in which we can try to get information about neutrino masses. Cosmology in the past years has become a very powerful tool to actually do so. Now, in the CMB, pre-Planck, the way to constrain masses, in particular from Planck, was to look at the impact on the change of the time of matter radiation equality. And this would lead to an enhancement here of the peaks and a shift due to the change in the sound horizon of the peaks of the CMB. Now, and the bounds that one could find were typically of the order for the sum of the masses of around 1.5 EV with WMAP. Now, Planck has changed that, has improved significantly on these bounds, down to 0.66 EV at 95% confidence level by looking at the lengthening of the CMB signal. Now, notice that this is the sum of the masses. We are in the quasi-degenerate regime, which means that each mass would be 0.22 EV. So already, this would tell us that Catherine should find no signal. And so that would be very interesting to see what actually Catherine finds and see if there's a compatibility or not between the cosmological observations and the direct measurement of the neutrino masses. Now, here you see their probability as a function of the sum of neutrino masses. And there is some dependencies on the assumptions that one makes. For example, if one weakens the impact of the lensing, then one sees that one can go to higher values of the masses. So one has to keep in mind some dependence there. The other very powerful probe is the meta-power spectrum. Now, neutrinos, they become non-relativistic, as I said already, when the temperature drops below their mass, but they still remain quite fast-moving particles, and the structures cannot grow below their free-streaming length, which is typically at quite small scales, 0.11 inverse megaparsecs. Now, as you see here, first of all, the impact is purely gravitational, so there's no dependence on the mixing angle, there's only dependence on the masses, and there's no way to distinguish the different components, the three different neutrinos, so it will depend on the sum of the masses. Now, if we look at EV neutrinos, this will give a contribution to the energy density of the universe around 10%. 1%. And then, so that could be somewhere 10% of the dark matter contribution, so this F nu factor. And here you see the suppression of the meta-power spectrum when I go from a 10% of the dark matter density down to a 1%. So you see there's a quite large effect you see here directly into on the power spectrum. Now, clearly what we have to do is measure the meta-power spectrum, or reconstruct better the measure the meta-power spectrum at quite small scales. There are various ways to do that. One can use galaxy surveys. This has been used already quite a lot in combination first with WMAP and now with Planck, to put constraints which are down in the 0.1, 0.2 EV, again for the sum of the masses. So for what I said before, 0.1 EV corresponds to inverted hierarchical spectrum, where I sum the two heaviest masses, which each of them is 0.05 EV. So their sum is 0.1 EV. Now, if I can go lower than that, then I can start distinguishing if instead the spectrum is with normal hierarchy. In that case, I have only one heavy mass, which is 0.05 EV. So between 0.05 and 0.1 EV is the difference between normal hierarchy and inverted hierarchy. Now, another way to trace the underlying meta distribution is looking at the intergalactic low-density gas through the Lyman alpha forest, or through the 21 centimeter lines due to the neutral hydrogen, first at the high redshift in the intergalactic medium, and then at lower redshift in dense clumps. And all of this, I mean, there's a very wide literature. Here I report only some references. But there are two main issues which need to be kept under control. One is the bias. Now, you are measuring something which is visible, for example, the galaxy distribution. Now, that needs to be related to the underlying meta distribution, which is really what we are interested in. And that is done through the bias. So we need to know the bias and have that under control very well if we want to extract the information about neutrino masses. The other issue is that now we are going into a regime in which the growth of structure is highly nonlinear. And so we need to trust both the theoretical understanding and the n-body simulations, which somehow have started a few years ago, including neutrinos, and somehow are developing further in this direction. The other way to look at neutrino masses, and in particular the meta-power spectrum, is through lensing of galaxies. So, and this allows to reconstruct the integrated density profile of matter between the galaxies and the signal that we observe. Now, this is going to be extremely powerful. There are forecasts for the use of Euclid, for example, which can bring down the measurement of neutrino masses in this region which distinguishes normal versus inverted hierarchy. So again, we are looking at very small scale. So again, here, the theoretical understanding need to be at the percent level. And this is, for example, a forecast in which shows the measurement of the sum of neutrino masses versus the energy density in relativistic particles measured through the N-effective, the extra number of the neutrinos. This is a forecast for kind of small values, and you see how well you could reconstruct when you combine Planck with the cosmic shear, so weak lensing, galaxy clusters, and galaxy surveys. So in principle, as they depend on different parameters, you should be able to break the generacies and measure this down very well. As I already mentioned, this is another parameter which is very important, which is the expansion of the universe. And again, I think that's actually a very important effect to consider, as there could be different evolutions, so different sources, depends on the origin of the accelerated expansion. And so this is not a forecast, this is actually measurements using Planck data and combining that with galaxy surveys. And you see that as I include the dependence on the value of W, and even more so if I include some redshift evolution of W, then this kind of weakens the constraints on the sum of the masses. So it's very important to use different probes, as different probes depend on different parameters in different ways, and so can constrain much better these the neutrino masses. Thanks a lot. So now I'll use the remaining 5 minutes to put together particle physics and cosmology. So what can we learn if we now look at the complementarity of these searches? But I have to say, I think because the kind of implications that it has could be really groundbreaking, in particular if one can discriminate between Dirac and neutrino masses, then one has to be very careful that systematic errors are under control, and that one keeps in mind the type of model dependence, so all the assumptions we go from, both from the cosmological point of view in terms of the underlying cosmological model, and also in the case of particle searches, as I already mentioned, for example, in case of neutrinoless double beta decay. So, but assuming that all of this under control, so we can really rely and believe in the measurements that have been obtained on neutrino masses. So, well, the first case would be if, so Catherine starts data taking, at least they expect to start data taking at the end of 2015. So in few months, they actually could observe a measurement of a neutrino mass. And now, as I said, this is extremely robust. So this would mean that neutrinos have a mass of some fraction of EV. Now, in the case of neutrinoless double beta decay, we have a prediction for the effective Majorana mass parameter, the parameter that you can determine by looking at the decay rate, between this measured mass multiplied by 2 cos theta solar. 2 cos theta solar is roughly 0.2, 0.3, and the value of the mass here. So we have a quite well-defined range. The range comes, as I discussed before, by the fact that I don't know the CP violating phases. But let's say that the observations from neutrinoless double beta decay are compatible with that. There will be already some tension here, because now neutrinoless double beta decay experiments can go down to 0.2 EV in mass, so this upper bound here. Now, from cosmology, we expect that the sum of the mass is going to be 3 times this value here, so bigger than 0.6 EV. Now, if somehow we are right at where Planck has its bound, 0.66 EV, then if everything is compatible, we would know that neutrinos are Majorana particles. At lambda CDM, at least from the point of view of the impact of neutrinos, is a good model. Now, what happens if instead, for example, if we trust Planck plus galaxy surveys, the bounds are stronger than 0.6 EV already? Now, there must be some new effects in cosmology which somehow either mask the effect of the neutrino masses or have got rid of neutrinos. Now, the problem is that the neutrinos, for example, could decay or could annihilate into other particles. Once one tries to do that in a real model, one introduces new interactions, new degrees of freedom, typically relativistic degrees of freedom, so there are additional constraints coming in. So indeed, it's not so easy to find models which can get rid of the impact of light neutrinos from a particle physics point of view. If instead the neutrinoless double beta decay doesn't find what we expect from the measurement from Catherine, then in that case we can have 2 possibilities. Either neutrinos are Dirac particles, this requires no information from cosmology, or there are cancellations between the light neutrino contribution and the heavy neutrino contribution to neutrinoless double beta decay. One could think that theoretically that's very unlikely, but there are models, they are not the most preferred models from a theoretical point of view, but they are there, which can give very easily cancellations. For example, if I have a very low energy seesaw, the contribution exactly cancel out, and one will never be able to see neutrinoless double beta decay. But in that case, one has light sterile neutrinos, and there are other searches that one can, in which way one can look for them. Now, let's say that Catherine doesn't find anything. Now we have two possibilities. The ordering can be either normal or inverted. And in particular, let's look at the inverted ordering. Now, long baseline neutrino oscillation experiments are very sensitive to this and are going to give us a very kind of robust and precise answer to this question. So let's assume that in our future long baseline neutrino oscillation experiments, or even in ping war reactor experiments, Juno, we find that the hierarchy is inverted. Now, in this case, we have, first of all, predictions for neutrinoless double beta decay. If it is the normal hierarchical spectrum, in which I neglect the lightest of the masses, I have a range which is allowed for M effective. And let's say that we observe that. So first of all, we know the neutrinos are Majorana particles. Now we can look at cosmology. Now, if the spectrum is normal hierarchical, the two masses are 0.05 eV each. I sum them up. I expect the sum to be 0.1 eV. So if this is what the observation gives me, then I know that lambda CDM, again, from the point of view of neutrinos, works very well. But I could find that the sum of the masses is smaller than EV, so the same considerations that I made before would apply in this case. There need to be either some particle physics effect, new interactions with which we can get rid of neutrinos in the early universe, or there's some additional extensions of the lambda CDM which mask the effect of neutrinos, or there could be, we could even find that the sum is bigger. So then in that case, either we are not in the normal hierarchical spectrum, because you remember there's always an intermediate region, some partial degeneracy between the masses. In that case, the sum could be higher, but this would give me very important information about neutrino masses. Or there could be some new source of hot dark matter. For example, the simplest case would be to have some sterile neutrinos around. Now, from the point of view of neutrinoless double beta decay, now, if we look at a signal which is not compatible within the range, if it is smaller, then again, we expect neutrinos to be, as before, either Dirac particles, or there's some cancellation that we could hopefully be able to test. Or if they are higher, then it means that there's some additional contribution to neutrinoless double beta decay, which is not due to light neutrino masses. And then the other case is the case in which I have, let's assume that instead I have observed the other hierarchy, the normal hierarchical one. So we can draw very similar conclusions. I would just want to point out the case in which now really the synergy between neutrino mass searches in neutrinoless double beta decay and cosmology is crucial. So let's say, for example, that we see the prediction for MEE is in the tens of milli-electron volts. Now, but if you remember what I said before, there is that region in the normal hierarchical spectrum. Remember where in the M effective there is that cancellations which goes down, and then the predictions go up again. Now, by cosmology, we would be able to tell in which of these regions of the masses we are, so I can get very precise predictions for M effective, and then I can compare that with the data in neutrinoless double beta decay. And so, for example, I see an incompatibility there, that again, that would point towards Dirac particles. So I think the interplay is very important, and I come to my conclusions. First of all, both from an experimental, phenomenological, and theoretical point of view, determining neutrino masses is crucial. This has become one of the most important questions in particle physics since the discovery of neutrino oscillations in 1998. Now, the information we can get can come from different sources. I mentioned long baseline neutrino oscillation experiments, neutrinoless double beta decay, where the masses come in combined together with the CP varying phases, and beta decay, which is the most robust, but also somewhat the least sensitive of these probes. But there again, we have Catherine, which is going to start in a couple of years, 2.5 years or so. And then we have cosmology, which in the past 6-7 years has started playing a very important role in all these searches, and now comes in with information which is as stringent as the one which comes from particle physics. And it's by combining these different sources and looking at their compatibility or not that we can try to pin down if the standard picture for neutrino masses from cosmology and from particle physics is correct. And if not, we can try to understand how we have to extend both the standard model of particle physics and or possibly the cosmological picture. Thank you very much.